P plus and the sign of the energy, which I was not able to answer on the spot. So let me just make a comment about it. So we have that P minus is 1 over 2P plus Pi plus M squared. And you would say, well, if P plus takes all possible values, you get positive and negative energies. And then, well, you must think how you address this. And indeed, that happens. And what one has to do is to take P pluses to be just positive. Now, that will basically get rid of all these negative energy solutions. So let me, it is a little disconcerting actually how that happens, but let me do a simple example in which you have just P1 and P0 here. Just a two-dimensional world with a P1 and P0. And then the hyperboloid of solutions of the equation P squared plus M squared equals 0 is, well, minus P0 squared plus P1 squared is equal to minus M squared, or P0 squared minus P1 squared is equal to M squared. And that gives you this usual with M and minus M. And indeed, you realize that if you want to solve for P0 as a function of P1, you have to take a square root. And for any value of P1, you get one positive square root, one negative square root. And one is the positive energy solution, one is the negative energy solution. And our physical particles are associated with positive energy. That's, in a sense, much of what quantum field theory does. Quantum field theory, for you, teaches you a way to sort of start with these things that have positive and negative energy solutions and results in particles that just have positive energy. So you say, well, you take the square root here, and you get two things. But if you're in the light cone, you never take square root. So how does this show up? How do you get two branches if you're in the light cone? You're never taking a square root. And the answer is simpler than what you may think. Let's realize that just this axis here are the P plus axis and the P minus axis. You see, this is P plus because on this line, P minus is 0. P1 is equal to P0, and this is the P minus axis. And if you're in 2 dimensions, then basically the only thing you have here is that P squared is minus 2P plus P minus equals minus M squared. And therefore, from here, you get that P plus P minus is equal to M squared over 2. And you remember, that's also the form of a hyperbola. If you have xy equal a constant, you do get 2 branches. You get this and this. So this equation has 2 branches. And if P plus is positive, you get this whole branch. This whole branch of these positive energy solutions are with P plus positive. And therefore, the way the branches appear in the light cone is when you make the transition for P plus positive to P plus negative. So when you want to represent a physical particle, you must take P plus equal positive. So if you have more questions about this, we can do them later on. But at this moment, I want to resume what we were doing last time. So we had decided that we're going to have Schrödinger operators for the point particle that were going to be xi, x0 minus pi and p plus, commutation relations xi with pj equals I delta ij, and x0 minus with p plus equals minus I, and a whole collection of defined operators. And one was x plus of tau, was not an original operator, it's expressed in terms of the operators you have. I don't put hats on these things. Everything, you recognize what are operators. Tau is not, m is not, but everything else is. And p minus was 1 over 2p plus pi plus m squared. So these were defined operators from the list of operators that you started with. And we then decided that we're going to have Heisenberg operators. And any Heisenberg operator, we're going to evolve. Tau is going to be like our time. Tau is going to be the parameter. So every Heisenberg operator, in principle, can have tau dependence. The thing we want to do now is to invent a Hamiltonian. But why do you say you should invent it? Well, you don't have to invent it, but then you have to study all kinds of methods of constraint quantization, because it's a system with constraints. So the best thing, and really what most people do, is just try to guess a Hamiltonian, because either it's very simple or it doesn't exist. So when I say that we're going to invent it, we want this Hamiltonian to be such that its Heisenberg equations of motion of the operators will be like the classical equations of motion of the particle. You know, the particle just is free, it's not very complicated. This xi, the classical solution, depends on pi and things like that. So we can sort of guess what the Hamiltonian is. Hamiltonian. By saying, well, if I wanted to evolve things with respect to x plus, I would use p minus as the Hamiltonian, because that's the energy. But I want to evolve things with respect to tau. So dd tau is really not quite ddx plus, but pretty close, dx plus d tau. They're proportional up to a constant. So dx plus d tau is p plus over m squared, ddx plus. So my guess is that the thing that evolves in tau, or the logic, should be this thing, and the thing that evolves in ddx plus, which is p minus. So maybe our Hamiltonian should be simply p plus of tau, p minus of tau over m squared, because it should evolve in tau, and therefore it's this thing times the thing that evolves in x plus. So this is like a guess. Our job is to make sure that this does the right things. And it's, as I tend to emphasize, is the art of constructing Hamiltonians. It's most of the times you really have to try to figure out how to do something that makes sense rather than follow a recipe. But now we have here that we can take the Hamiltonian to be, well, this thing. So what is p minus times p plus? You should put a tau here if you want for this, for the Heisenberg operators. These are the Schrödinger operators, time-dependent Schrödinger operators. So p plus times p minus over m squared. The p plus cancels here, so we get 1 over 2m pi of tau plus m squared. We're doing Heisenberg Hamiltonians. So, whenever you have a product of Schrödinger operators, the Heisenberg operator is the product of the corresponding Schrödinger operator. So here, from here, you would have that p minus of tau is equal 1 over 2p plus of tau times pi of tau plus m squared. So here is our guess, and let's see if it does anything right. In order to check a Hamiltonian, you look at the equations of motion, which are I d psi of tau d tau should be equal to psi of tau h of tau. This is the Heisenberg equation of motion of quantum mechanics. Yes, John. M squared here. M squared, 2m squared. Here must be m squared. And I hope I don't, yeah, it's m squared. I'm just making a typo. Thank you. If you have a Schrödinger operator that is, if you have a Schrödinger operator psi, then there's a Heisenberg operator psi of t that has of implicit time dependence, and it satisfies this equation of motion. This is from the definition of Heisenberg operators. If you haven't used that for a while, you might have forgotten it. The book, there's a little review of Heisenberg operators and Schrödinger operators. Now, if your Schrödinger operator initially has some time dependence, like this operator's here, this is a Schrödinger operator with some explicit time dependence, then this equation has an extra term that is of the form, I'll put it in parentheses, sometimes it's needed, plus I d psi dt. And this is really, this derivative really means the differentiation with respect to the explicit tau in psi, in psi Schrödinger. So these operators, for example, have no explicit tau dependence because the Schrödinger operators have no explicit time dependence. These two operators have explicit time dependence because the Schrödinger operators has explicit time. So when you want to find the Heisenberg of this, there's this explicit time, and this p plus may become p plus of tau because every operator becomes time dependent. So it's a little delicate, but it's really not that difficult, but you have to beware of what you're doing. So let's see the following things. Let's do 3 operators at a time. I dd tau, I'll calculate of p plus of tau, of pi of tau, and of x0 minus of tau. So this should be equal. These are these operators that are here, xi, pi, p plus. All these ones for which only one term exists. So I should do the commutator of either p plus of tau, pi of tau, or x0 minus of tau with h of tau. So these are 3 equations. And now let's look at it. Here is h of tau. The same commutators that hold for the Schrödinger operators hold for the Heisenberg operators. That's another fact. If x and p give you I, then x of tau times p of tau commutator give you the same I. So look here. P plus commutes with H because P plus commutes with the P's. Pi and Pj commute. There's no such commutator. So Pi's commute with H, and x0 minus commutes with H because x0 minus only commutes with P plus. And look, the P plus disappeared from H. So all of these are 0. So they are really operators without even Heisenberg time dependence. In the Heisenberg picture, these operators are constant, which is good. That's what we wanted. For the free particle, P plus, Pi were a constant. X0 minus was a constant of integration. So this is very good. So instead of writing P plus of tau, we can write P plus, even in the Heisenberg picture. Instead of writing Pi of tau, we can write Pi. And instead of writing x0 minus of tau in the Heisenberg picture, we can write x0 minus, and that's all because we wrote a decent Hamiltonian. So even at this moment, with all this, the Hamiltonian, you see, the Hamiltonian seems to have tau dependence, but in fact is, as a Schrödinger operator, would be something without explicit time dependence. So if you put here this for psi, the Hamiltonian itself, you would have Hamiltonian with Hamiltonian, which is 0. So the Hamiltonian should be time independent. The Heisenberg Hamiltonian is time independent if the Schrödinger Hamiltonian has no explicit time dependence. So at this moment, even this Heisenberg Hamiltonian is time independent, which is obvious because all these things are time independent. So h of tau now can be written as h equal 1 over 2 m squared pi plus m squared. So things are going well. But now let's do another thing. Let's do an equation that really should give something more substantial. So what is I dxi d tau? Let's see if we get something a little more interesting, because this is pretty much the only thing that has some important time dependence. So this should be equal to the commutator of xi of tau with 1 over 2 m squared pj, or yeah, I call it pj plus m squared. That's the Hamiltonian. Now, xi with pj is a non-trivial commutator, and that gives you an I. So there's 2 of those, and there's a 2 here. So you get I pi over m squared. And you should say, oh, that's exactly right, because that gives you the dxi d tau is equal to pi over m squared. And that was a thing we had in the classical theory, that pi is the momentum associated with xi, and therefore xi of tau can be written as a constant x0 I plus pi tau over m squared. It's a solution of this equation, and it's exactly what we had and in the classical theory. And moreover, since this should have a non-trivial commutator with pj, this x0i has a non-trivial commutator with pj. So x0i pj is I eta ij, or delta ij, I wrote. So this is good. You can try a tricky one, I dx plus d tau. You say, wow, but x plus is a Schrödinger operator with explicit time dependence, so I need the whole thing, this whole thing with the extra term. So you would have that this is I dx plus d tau, the last term, plus x plus of tau with the Hamiltonian. Well, this gives you pretty much all you want, I p plus over m squared, and that's what you're expecting. And this x plus is p plus tau over m squared with h, and p plus commutes with h. There's no x0 minus in h, so this is 0. And you get what you expected, that dx plus with respect to tau is this. So this is good. So this Hamiltonian seems to do pretty much everything we wanted to do. You could check more things, but they all work well. So this seems to be the Hamiltonian that quantizes the theory. And therefore, the next step is to introduce states. You have a Hamiltonian, and what did you have at the end? You have canonical variables, x operators, x0i, say, with pi, a pair of operators that don't commute, and x0 minus and p plus. So the states of a system are characterized by saying that they're eigenstates of some operators. So you cannot have them eigenstates of all these 4 operators because they don't commute, but you can have eigenstates, say, of the momenta. The pi and p plus commute, so you define states to be things p plus, pt, and if these are, as we want, to be physical states, they're going to, well, we're going to say something more about them. So what happens with these things? These are eigenstates of this operator. So if I write the eigenstate equation, I should write it a little maybe with a hat, not to confuse you. P plus, P transverse. So the P plus operator acting on this thing is equal to P plus times the state. And the P transverse operator acting on these states is P transverse, the vector, acting on the states. So these are the states of your theory. So you can also ask what is the P minus operator acting on these states, and the P minus operator acting on these states, P plus, P transverse, is equal to, well, the definition of a P minus operator is up there. So it's just Pi's and P pluses. So it's 1 over 2P plus P transverse plus M squared on the states. So we want to declare these states to be the physical states of our theory. So given the remarks we had before, we consider these states with P plus positive. And these states are particle states. They're the state of a particle with momentum P plus and P transverse, and with momentum with P minus eigenstate. It's an eigenstate also of P minus, and it has the eigenvalue being the light-con energy. So you've discovered particle states, and then you realize that when we discuss the light-con quantization of the scalar, we had A P plus P transpose, like that, dagger on the vacuum. These were the one-particle states of the scalar field theory, and these are states with exactly the same label. So there's a one-to-one correspondence between these states. For each state here, there's a state here. These states were particles with momentum P plus and P transverse and energy P minus, and these are the same thing. So what you've really done here is discover that the quantization of the relativistic point particle gives you particle states that are identical to the particle states of the scalar field theory. They're the same particle states. So this is a pretty remarkable result. This is a quantum states of the relativistic point particle, quantum states of the relativistic point particle. And this is quantum states of the scalar field theory. But they represent the same physics. Now, barely on time to not get too behind. I have some things to finish today for your practice problems in the afternoon. But I want to make a few remarks here because this is actually something that people say all the time, and maybe you've heard it, and it's a nice sort of way of encapsulating all the ideas together. In the scalar field theory, we also had multi-particle states, A, P plus 1, P transpose 1, dagger, A, with several oscillators. These were multi-particle states. But in the relativistic point particle, we just got one state. You see, the labels are there in the vacuum, and there's no operators in the theory that you can act to create more things. Or here the labels are in the operators, and therefore you can create more and more states. So is it the same theory after all? Because this theory has multi-particle states, and this doesn't seem to have them. Well, it may be a little bit of an issue of semantics. Most people say these are the same theory, but this is a more complete or more manageable version of the theory. This is what is called first quantization. This is what we call second quantization. And let's make that even more clear. So suppose you're in the point particle. You can write a Schrödinger equation. So how would you do it? Well, you're in the point particle, so you define now a general state. How do you define general states? By superpositions of this state. So you put integral dp plus the integral dp transpose and a wave function that depends on tau, p plus, and p transpose. That's a general state of the particle, point particle. That's how you define a general wave function. So then you try to say, well, the Schrödinger equation should be e to I ddt of psi of t should be equal to h psi of tau. This is all tau, I'm sorry. So let's look at what we get. If we do dd tau of this thing, the dd tau goes into the psi. The h operator is there, is pi over 2m squared. So the h operator comes in here, goes through the psi, doesn't care, goes to the state and puts pi over two things, over 2m squared. So from this equation, we get I dd tau of psi of tau p plus p transverse equal 1 over 2m squared, p transverse squared plus m squared, psi of tau p plus p transverse. So you should do it, but it's sort of clear, and that makes sense. This is the Schrödinger equation for the relativistic point particle. Now let me remind you of the scalar field equation. That was d squared minus m squared phi equals 0. Well, let's look at it in the light cone. This is minus 2 ddx plus ddx minus plus ddx transverse minus m squared times a phi that depends on x plus, x minus, and x transpose equals 0. Now I want to Fourier transform in x minus and xt. So we'll write phi of x equals dp plus dp transpose e to the minus I x minus p plus, you're Fourier transforming in x minus, plus I x transpose p transpose, phi of x plus p transpose. And now I substitute here to get this equation in momentum space, in whatever momentum space I've done. Sorry if it's going a little fast with the calculations, but they're not difficult. You just differentiate and you see this. So what do you get? Minus 2 ddx plus times minus ip plus. In fact, I'm writing down a lot of details. Dx transpose will give you p transpose squared plus m squared phi of x plus, x minus, and p plus and p transverse, I'm sorry. So here is the equation so far, and finally put that x plus is equal to p plus tau over m squared, which is our relation for this. And therefore, this ddx plus will become a dd tau of something, and this p plus will be here. And you just put that in and simplify, and what do you get? You get I dd tau minus 1 over 2m p transverse squared plus m squared phi of tau p plus p transverse equals 0. Okay, look, I did a lot of massaging to this simple equation of the massless scalar field. And by the time I wrote it in terms of the right variables, it has become identical to this equation if psi is identified with phi. So actually, that claim that these two things are deeply related is even more clear here, in that the Schrödinger equation for the particle wave function is the same as the classical field equation of the quantum field. That, yes. It's the right one. So here is m squared, because there's m squared, so I get an m squared here. Thank you. So I'll say it in a way with boxes, what people usually say here, which is a nice thing. That you begin with classical mechanics of x's and p's. And you do first quantization. And what do you get? X hat operators, p hat operators, and one particle states. That's what we got here, only the one particle states. Then you say, look, let me get the Schrödinger equation. So from here, I get the Schrödinger equation. And then you identify it with the classical field equation of a field, phi. And then you do second quantization. In the sense that this was the first quantization, this is the second quantization, and you get field operators and multi-particle states. And this is the story of first quantization and second quantization. And one of the key steps is that the Schrödinger equation becomes the field equation. And this really happens in the light cone in a beautiful way, because the Schrödinger equation, as you know very well, is the first order in time. And only in light cone, the equations of motion are first order in time. So in covariant quantization, this analogy is not all that perfect. So most people think that the first quantized theory is a primitive theory, and the second quantized one is a better version of the same theory, a more practical version, because you can deal with multi-particle states, with interactions better, and all these things. Yes?
Quantization of a relativistic point particle was not possible, but apparently that's concluded.
First quantization of a relativistic point particle is not possible?
Yes, I heard that if you would try to write a relativistic version of a one particle wave function, that it would somehow not work, that would always run into problems. But that's not true. Okay.
No, the first quantization of a point particle is perfectly okay. The first quantization of the string is perfectly okay. And we'll do a similar thing for the string. We'll see how all the particle states arise. So this is a nice story, but it's not the end of the story for the... Yes, sir.
Sorry, why does it only work in the light cone coordinates?
Well, it's clear in the light cone coordinates because there's a Schrödinger equation is first order in time.
Yeah, I mean, so if they just go to normal coordinates and write the Schrödinger equation for the relativistic type, no,
well,
you should get the same result.
No, it's a little different. It sort of comes through a constraint in that case, not through a Schrödinger equation. I'll discuss it with you later if you want. It really has to do with covariant quantization. But you see, your usual equation, like d minus m squared, this is all I want to say now, would be d second dt squared plus box, or minus box, on phi. So the classical field equation in conventional coordinates is not the Schrödinger equation. Only in light cone case it's a Schrödinger equation. Okay. Light cone, momentum, and Lorentz operators. I like very much this part of the discussion because, in a sense, here already something very non-trivial has happened. You suddenly see that your classical field equation is the same as the Schrödinger equation. It's pretty striking. But before, we seem to have been putting all what we need to get the classical field theory, and we just got it, and you say nothing. But with these light cone momentums and Lorentz operators, they're going to turn out to be cleverer than what we are. we're going to try to do something, and it's going to look like things don't work. And then when you look at it, you realize that they work better than you could have expected even. And the theory didn't allow you to walk off the cliff, pretty much what's going to happen now. So it's a curious thing. So let me discuss now for a second covariant quantization as a way to illustrate what these operators should do. So in covariant quantization, even time the x0 coordinate is an operator, and time is not an evolution parameter anymore. So it's a funny thing, but nevertheless, in covariant quantization, you would write this. And you would also say that p mu of tau, p nu of tau, the momenta commute and the coordinates commute, but in particular, the momenta commute. Now, if momenta generate translations, they better commute. So how do momenta generate translations? Delta x mu of tau, say equal to epsilon mu. In a quantum theory, any symmetry transformation like this, the translations of a free-point particle, is generated by commutators. So we claim that delta x mu can be obtained by commuting a momentum operator with x mu. So the momentum, we say, generates translations. And if we do this commutator, we certainly get I epsilon nu, and then these two things that give you minus eta mu nu I. So you get epsilon mu, indeed. So this is fine. Now we have in the light cone operators p plus, p minus, and p I. And none of them is time dependent, no time dependence. That's why I don't write them. The Heisenberg operators are not time dependent. And they all commute. They commute. Our postulate, so this part is good. This thing is correct. Now, we don't expect this to be correct because that's not how we set up the commutators of x and p. But if these are honest momenta, they better generate something like translations, and we should understand whether they do so. So I want to see if they generate translations. So I ask, is delta x mu really given by this thing acting on x mu? So this thing would be minus I epsilon plus p minus I epsilon minus p plus I epsilon I pi with x mu, possibly of tau. So I want to see if this formula, if things generate the right things or not. Certainly, at least we got the right algebra of momentum operators, and that's fantastic. That didn't take us any work. So here I'm going to do a couple of cases. Case one, there's only an epsilon minus that is different from 0. So then delta x mu should be given as minus I epsilon minus p plus commutator with x mu of tau. Now, an epsilon minus difference from 0 should generate, you expect, is a translation, is that right? Generate delta x plus equals 0, delta xi equals 0, and delta x minus equal epsilon minus, because it's a translation in the minus direction. That's what it should do. So let's see if it does. Delta x plus would be minus I epsilon minus p plus with x plus, which is p plus tau over m squared, and p plus with p plus is 0, so that's good. How about delta xi? It's minus I epsilon minus p plus with xi. Well, xi is x0 plus pi tau over m squared. So xi is x0i plus pi tau over m squared. Now, and p plus commutes with that. That's 0. Very good. Delta x minus should be minus I epsilon minus p plus with p minus, with x minus, I'm sorry. So this is x0 minus plus p minus tau over m squared. And p plus with x0 minus is minus I. No, it's plus I. So you get minus I epsilon minus times an I. And that's epsilon minus. Perfect. All these translations work. So let's do another one. Case 2. Only epsilon plus different from 0. Okay. So in this case, delta x mu would be equal to minus I epsilon plus p minus, I epsilon plus p minus, I'll write what it is, 1 over 2 p plus pi plus m squared, x mu of tau. Well, what should we get? So we expect this time that x plus, delta x plus to be just epsilon plus, delta x minus to be 0, and delta xi to be 0, because it's a translation in the plus direction. Okay, let's see. Well, delta x plus, let's do that. X plus would be minus I epsilon plus this whole thing times x plus, which is p plus tau over m squared. Well, we should get epsilon plus, but p plus commutes with everything here. Get 0. Oops. Doesn't seem to be translating. Okay. Let's do delta x minus. It's minus I epsilon plus 1 over 2p plus pi plus m squared, x0 minus plus p minus tau over m squared. So we've put x minus there. And this one should be 0. We shouldn't translate it. Let's see. P minus, so certainly commutes with this thing. It's also P minus. Good. X0 minus commutes with the PI's, but it doesn't commute with P plus. So actually, it's not 0, this whole thing. Okay, we can do that commutator. I'll leave it up to you to do it. It's not hard, but you get epsilon plus p minus over p plus. So this one didn't work. This one doesn't work. And delta xi, well, xi contains x0i, so it will not commute either. It also gives something. Let's record what it gives. It actually gives this, epsilon plus pi over p plus. So at this moment, you would say, nothing works. It's gone really crazy, this thing. And what is this? Now, you should, if you were doing this the first time, you probably get a little nervous, but you should not panic because your operators satisfy the algebra. P commutator is 0, so presumably they're doing something. But these operators are doing something very good, actually. You see, the Lightcon gauge, you impose the Lightcon gauge, and in which x plus was equal to p plus tau over m squared. If this would have gotten translated, after this transformation, x plus would have become p plus tau over m squared plus some e plus. And this is not Lightcon gauge anymore. So the theory actually refused to get you out of the gauge because you quantized in that gauge and the theory doesn't want to get out of the gauge. If you would have obtained this, you would not be in the Lightcon gauge anymore and it would be totally unclear what you're doing. So what did the theory do? What did this translation operator P minus actually do? Because the translation operator now is P minus. Well, the translation operator looked at the theory and said, I could do this translation, but then I'm out of the gauge. So maybe there's another symmetry that I can also do. Even though I'm called momentum, I may be able to do other things. And the thing looks at it and says, well, this was reparameterization invariant, so I can translate and reparameterize in order to bring it back to the gauge. So let's see if that's what this is doing. Reparameterization invariance is the idea that x mu of tau can be changed into x mu of a different tau, tau plus a lambda of tau, and nothing changes. So if you write this as x mu of tau plus lambda of tau d tau x mu, you can think as this as a symmetry transformation. Delta x mu of tau, lambda of tau d tau x mu. This is a symmetry. If you doubt this is a symmetry, you shouldn't doubt it too much because we've seen the point-particle action is parameterization invariant. If you doubt it, check what the Lagrangian varies when you do this transformation. And you will find that it goes into a total derivative, which is still good enough for a symmetry. So this is a symmetry. So let's postulate that what the translation operator does is a translation plus a reparameterization. So if it takes x plus, we'll take it to x plus plus epsilon plus. That would have been the translation, but then it reparameterizes it, so it adds lambda d tau of x plus. And this whole thing, to keep the Lightcon gauge, should be 0. So from this, we have that epsilon plus lambda d x plus d tau is p plus over m squared. should be 0, and that determines lambda for us. I need a little bit of a blackboard here. So let's see what lambda is. We're hypothesizing that this operator not only translates, but reparameterizes. So if that is true, lambda from that equation, you get that lambda over m squared is minus epsilon plus over p plus. Lambda over m squared is minus epsilon plus over p plus. Correct. So then, if this is true, what should have been the transformation of x minus? Well, it doesn't translate it, so it should be 0, but it should still reparameterize x minus, so it should be lambda d tau x minus. And what is lambda? Lambda d tau x minus is lambda, and d tau of x minus is p minus over m squared. And lambda over m squared is minus epsilon plus. Then you get p minus over p plus. And here it is, delta x minus. It's exactly that. That's what it did. Similarly, for delta xi, it wouldn't translate it, but it's still, the reparameterization holds d tau xi, so this should be lambda. D tau xi is pi over m squared, so you get minus epsilon plus pi over p plus, which is the other one. So there you go. The momentum operator P minus is very exotic after all in Lightgun, and it's very clever. It translates and reparameterizes. That's more than just translating. It still satisfies the right algebra, so it's good. And it translates as much as you could do in the Lightgun without going out of the Lightgun gauge condition. So in a sense, this operator did things more cleverly than you may have given it credit for. It was a real symmetry. It preserved the gauge condition. So it really produced a real symmetry of the theory. Now this story repeats itself for the Lorentz generators. Remember that we have Lorentz symmetries, Lorentz transformations delta x rho of tau equal epsilon rho nu x nu of tau. These were the infinitesimal Lorentz transformations. We discussed them a few lectures ago, and the conserved charges for this are Lorentz operators. Even though we wrote them for the string, they look even simpler for the point particle. These transformations arise in the quantum theory by commuting these Lorentz generators with the coordinates. So these transformations arise from the commutator of the Lorentz generators with that. We checked it for the translation. I will not check it here. So if you put here these things and compute using the covariant quantization, this works. And what do the m's, what algebra do the m's satisfy? They satisfy m mu nu, m rho sigma. You can compute their commutator is the Lorentz algebra. Probably you talked a little about it in quantum field theory. It has an I, eta, mu, rho, m, nu, sigma, plus 3 more terms. to implement the mu nu symmetry and the rho sigma symmetry. Now, this operator is manifestly Hermitian. This is the case because it's only non-zero if mu is different from nu, and in that case, p mu and x nu commute. So the Hermitian conjugate puts the p to the left of the x, but then it can be brought back because mu and nu must be different from each other. So it's manifestly Hermitian. Okay, so p minus was a very non-trivial operator. It was here, it generated translations in a funny way. The most non-trivial Lorentz generator involves a minus. Since it's antisymmetric, here you cannot have an m minus minus. That doesn't exist. But you can have an m minus I. So you would expect this Lorentz generator to behave sort of like the momentum operator. It will do a Lorentz rotation and as much of a Lorentz rotation to preserve the Lightcon gauge, and it will do a reparameterization to bring it back to the Lightcon gauge, and it will transform the other ones, and it should satisfy the right algebra. Now, if you look at this algebra and you put the signs, you will see that this commutator should be 0. And you would say, well, isn't that obvious it's going to happen? It's not obvious, because even though you read it from here, the commutators of the x's and p's in Lightcon are very different from the ones of covariant quantization. So even this is not obviously true. And in fact, in Lightcon, you wouldn't know exactly how to define this. It's going to take me one more minute to finish, so that's not so bad. This is the middle board. No, that is the back board. And the middle one goes here. So let's see, just get a little feeling of what's happening here. And again, this idea that physics is art. What should be m minus I? Well, if you say, well, I don't know what it is, in Lightcon things sometimes are strange, but the best guess is to try to do this. So your best guess is to put x minus of tau pi, pi doesn't have time dependence, minus x I of tau p minus. Okay, let's see what this is. This is x0 minus plus p minus tau over m squared times pi minus xi of tau, which is x0I plus pi tau over m squared, p minus of, like that. And p minus, you know what it is. It's a formula in terms of p plus. Well, these two terms cancel because p minus and pi commute. That's nice. It's simple. x0 minus pi minus x0I p minus. And, well, it looks so good. We should have trusted our intuition that this is right. But is it? Well, look, the operator is guaranteed to be Hermitian by that formal argument. Is it really Hermitian? Well, if I do the Hermitian conjugate, I get pi x0 minus, and if I bring them back, I can, because pi commutes to 0 minus. Yeah, this term is Hermitian. How about this term? p minus x0i. Well, p minus has all this pi squared, so it doesn't commute. So this term is not Hermitian, actually. So this is the kind of troubles you obtain when you go to the light gun. You think you're going to have a Hermitian operator, suddenly your operator is just not Hermitian. So what do we do? Well, invent something totally new? Probably won't work then. This probably wants to work, but it's just not Hermitian. So you try your best and you say, okay, pi minus 1/2 of x0i p minus plus p minus x0i. You make it Hermitian by hand. You take this thing plus the operator plus its Hermitian conjugate, and you divide by 2. In the classical theory, this would be probably the right thing to do because they're the same. So you hope this works. But you must check it. So this is the tentative expression for m minus I. And one must check that this algebra holds. And it does. It's not a very short calculation, but it does. It was left as a problem in the textbook. And what you will do this afternoon is to check that this generates the right transformations, the Lorentz transformations and reparameterizations that you would expect. In the string theory, we'll write the same operator, and again, we'll have to do things to make it as well defined as possible. And when you compute this commutator, it only is 0 if d is equal to 26. So actually, it's a very non-trivial constraint. So we'll leave it there. Hope good luck this afternoon with your practice, and we'll see you tomorrow.